All right, welcome to lesson 1.05. Today we're going to talk about the squeeze theorem, and we're going to use it to make sense of what might appear to be some pretty complicated looking limits, particularly with trigonometric functions. This theorem not only has a great name, but is really useful, so it should lend to some pretty interesting concepts. So before we get into the mathematical definition of the squeeze theorem, this little situation will help us get some intuition about what it is saying. Each day in the month of August, the following is true. Jesus squats at least as much weight as Tylen. Angel squats at least as much as Tylen and no more than Jesus. On Tuesday, Jesus squats 300 pounds, as does Tylen. How many pounds does Angel squat? So go ahead and give this a try on your own, and then we'll take a look. Okay, so there are many different ways you could start this off, and let's just kind of look at it from the situation that we have right here, and then we'll represent it using inequalities. So Jesus squats at least as much weight as Tylen, which means that Jesus could squat, at the very least whatever Tylen squats, but it's either that or it's more. Angel squats at least as much as Tylen and no more than Jesus. So again, whatever Angel squats, the least it could be is whatever Tylen is squatting, but it could also be more. And it can't be any more than what Jesus is squatting. So it could be the same, it could be equal to, or it's less than. So now let's consider this situation. We have Jesus, and he squats 300. And we have Tylen, and he also squats 300. So how much did Angel squat? Well, remember, Angel squats at least as much as Tylen. So the least it could be is what Tylen squats. And no more than Jesus. So it can't be any more than what Jesus squats. So the only option for us is that Angel also squats 300. And the reason for this is that when we read these two statements here, there was an inequality that was being made very clear. Jesus is squatting at least as much as Tylen, so greater than or equal to whatever Tylen is squatting. But then we find out that Angel is in the same boat. He's also squatting at least as much as Tylen, but can't be any more than Jesus. And so that allows us to represent it as such. And so when we know that Jesus is at 300, and Tylen is at 300. The only option is that Angel is also at 300, because it's the only value that is both less than or equal to 300 and greater than or equal to 300, because it's equal to both of them. And this is essentially the squeeze theorem, right? Angel is basically whatever he's squatting is being squeezed by the fact that it's got to be less than or equal to what Jesus squats and also greater than or equal to what Tylen squats. And since both of these kind of bookend squats are the same, it's squeezing whatever the value that Angel is going to squat into being 300. And so you can kind of imagine what this might look like with functions, particularly graphically, and that might give you a little hint as to what this squeeze theorem is going to tell us. So let's go ahead and take a look at it and illustrate it and then use it. Okay, so the squeeze theorem. It's also sometimes called the sandwich theorem, but whenever you're given the opportunity to use the word squeeze, you've got to take it. So we're going to call it the squeeze theorem, but if you're a particularly big fan of sandwiches, that's up to you. And here's what it states. If the function f of x is greater than or equal to a function g of x, which is in turn greater than or equal to a function h of x, when the x values are near some value a, but not necessarily at a, meaning that for x values that are near a, but at a, it doesn't have to be the case that this is true. And we know that the limit as x approaches this value a of f of x is equal to the limit as x approaches a of h of x, meaning they're equal to the same thing, we'll call it L. Then what we know is the limit as x approaches a of g of x is equal to that same value L. And you can think of this from the perspective of the situation that we just saw, right? We have a function f of x, which is going to be greater than or equal to this function g of x, and that function is greater than or equal to this function h of x. And so if the two bookend functions, we know that the limit of those functions as we approach this value a are equal to L, then what we can say is the function in the middle has to be squeezed into having the same limit value as x approaches a. Okay? So let's construct a graph, a graphical representation that will really help us understand what's going on. All right, so I've done some pretty nice artwork, at least by my standards down here, and what we have is these three functions that are subject to this stipulation, right? So what we have is we have a function f of x, and we notice that f of x, at least for all x values around a, is greater than or equal to g of x. And then we also have that h of x is going to be less than or equal to g of x for all these values around a. And we also know that the limit as f of x, as you can see, as f approaches a from the left and approaches a from the right, is equal to the limit as h approaches from the left and from the right. And I tried to draw these sort of on top of each other, if you can picture that, but I also wanted you to see each function, so it almost looks like they're layered, but you can imagine that they are all, that f and h both have the same limit, and so the limit as they approach a is equal to L. So this y value, the y value that they're approaching is L. So we can, this y value is L. And so it's pretty intuitive then that the limit as x approaches a of g of x is also going to be equal to L as we approach from the left and as we approach from the right. And that's pretty handy. And the reason it is because if g is some kind of unknown or hard to work with function, if we can just find a couple of functions that are going to be greater than or equal to, and in the case of h of x, less than or equal to g of x for these values around a, and then we can find the limit of f and h, then we've also found the limit of g as we approach a. Okay? So we'll look at a couple of different examples for how this is going to be super helpful, and the first of which is going to be a very basic, just something that you need to memorize. And I'm actually going to show us a couple of things that we need to write down and sort of commit to memory because we never want to have to prove them more than once. So we're going to prove them once, and then we'll commit it to memory, and we'll have the basic intuition behind it, but we probably won't in the middle of a test want to have to go through the derivation because that could waste a lot of time. Alright, so here are a couple of trigonometric limits that you'll want to remember. And the first is pretty simple. The limit as x approaches 0 of sine of any number n times x over x is equal to that value n. So n could be anything, 1, 2, 3, 4, 5, 6, 7, whatever it is. And then secondly, the limit as x approaches 0 of 1 minus cosine of x over x is equal to 0. So what you notice is that if you look at both of these, first off, these expressions not so pleasant looking. And secondly, if you were to try the substitution method by just plugging in 0, you're going to have an undefined function. It's going to be undefined. And so we'd have to think about manipulating these in some way. Okay? And you could, of course, use the table method to confirm these, but we're going to actually go through and prove. So notice here that it's whatever n is, it doesn't matter. And so let's just think about the most simple case, and that would be when n is equal to 1. And so what we're going to do is we're going to go through and we're going to prove that the limit as x approaches 0 of sine of x, 1x, over x is equal to 1. Okay? That's what we're going to prove. Alright, so here's our special case of that really helpful fact that we just saw, where we set n to 1. So the limit as x approaches 0 of sine of x over x is equal to 1, and we are going to prove this. So as you might have guessed, we just learned the squeeze theorem, and we are going to utilize it here. Let's think, and if this is kind of just a basic how-to for when we're proving something, is before we jump right in and start trying to mess around with things, we want a roadmap, right? So we understand what we're trying to prove, and now we want to come up with a plan, right? How are we going to actually get there? How are we going to take some things that we are aware of, that we know of, and eventually conclude what it is we're trying to conclude? And if we're going to use the squeeze theorem, we can just think about what we need to have in place so that the squeeze theorem tells us something. So if we're going to use the squeeze theorem on this function, what we need are two other functions that squeeze this function, so to speak, right? So we need one function that is going to be greater than or equal to sine of x over x for some x values around 0. And we need another function that's going to be less than or equal to sine of x over x for x values around 0. And then we need one more thing. We need both of those functions to have limits as x approaches 0, and we need to know what they are, right? Because then we'll know that that limit for those two functions is also the limit for sine of x over x. And, right, we obviously hope that the limit of those two functions as x approaches 0 is going to be 1, okay? So that's the roadmap for kind of bigger proofs, and as you go on to college and whatnot, you'll actually spend a lot of your time sketching out these plans for proofs. And that can save you a lot of time, because if you jump in and you start writing it out formally, that's going to take a lot of time. And so if you can just sketch out what you're going to do first and say, oh yeah, I think this works, this makes a lot of sense, and then spend your time writing it formally, you're going to save a ton of time. Just like with any problem that you're solving. If you have a plan first, it'll be helpful. The next thing I want to say is about this proof. I remember when I saw some of the first proofs in calculus when I was in college, and I thought to myself, wow, it's really incredible. How on earth could someone come up with this? How dumb must I be that I would never think of doing something like this? And what you have to do is realize that the person that proved this, they didn't spend 5 minutes on it. They didn't spend 5 hours on it. They spent a long, long time on it. Because it's important enough that it show up in our, calculus book or whatever it is that's taught all over the world. Chances are someone didn't spend 5 minutes on it. They tried many, many different things. They failed, hundreds of times, and, maybe once they thought they had it and someone finally said, oh, no, you spent 6 months and it actually isn't logical. And they went back and reworked it. And so don't worry about the fact that you might not have thought of this method on your own. Instead, view it as another way in which you could view something. So learn from the way that this is proved, and maybe you might be able to apply it at some later point in life. So for this proof, we need to think about a couple of functions that might be either greater than or equal to or less than or equal to the sine of x over x. And before we jump in, we want to think about what is the sine of x. Where does that live? How do we define it? And the sine of x is defined by the unit circle, right? It's the y coordinate of points around the unit circle. And so it might be a good place to start to take a look at the unit circle and see if we can't come up with a couple of other things related to the unit circle that might squeeze this function sine of x over x. So that's what we're going to go. So it's time to get your circle drawing device out and sketch a nice unit circle. Alright, so here's my unit circle, and I've drawn just in our first quadrant, an angle of x. It's a generic angle, right? I want to make sure that I solve it as a generic angle so that it works for any angle x. And now we've got to think about, alright, I want something involving the sine of x. So what is the sine of x in relation to my angle? Well, remember, the sine of x is the y value of this point here where it intersects the unit circle. And the y value can be thought of just as this distance here from the x-axis up to that point. All right. So we have the sine of x, and what we're going to try and do is somehow involve the sine of x in an inequality that will squeeze, hopefully we can create this function here at some point. We'll squeeze that function. So notice that we have what's taking shape as sort of a bunch of geometric shapes. And what would be really nice is if we could actually find three shapes which, in the unit circle are going to squeeze one of the ones in the middle. So what I want us to kind of look at is, okay, we have, for any angle x, we first off have the kind of slice of the unit circle that it takes into account, right? That it cuts out. Now what else do we have? Well, it would be nice if we could involve sine of x in some way. And maybe we think about constructing a triangle involving sine of x. Okay, well if we want to compare the areas of triangles, we need the base and the height of the triangle. And so what kind of a triangle could we construct where we know the height is sine and the base? Well, it would be really nice if we could utilize the fact that the length out to the end of the unit circle is 1. So what if we constructed a triangle that had this shape? Its height would be the sine of x and its base would be 1. Okay, great. So you can kind of visualize that. And then is there a shape that's maybe a little bigger? And yeah, you have this pi slice, this part of the unit circle that's been taken up sort of by the angle. And then we need one more bigger triangle. And so maybe if we want a bigger triangle, we could come out here and drop something down. And again, we want to make our lives easy. So let's try and pick a base length that we maybe already know. So maybe we create a triangle here where the base is 1. And so then we only have to figure out whatever that height is. Alright, so let's go ahead and do that. Let's make our first task figuring out what the height of this bigger triangle is going to be. Alright, so here is the height of this larger triangle. And what do we know about this larger triangle? Well, we constructed it so that we knew the base was 1. That's important. And now let's think about what will the height be. So I'm going to let you try this on your own, and the hint that I'm going to give you is something that I repeated over and over and over again, told you would be a useful fact, is the slope. We know the slope of this terminal side of any angle. So what we know about this terminal ray is we know the slope. The slope we've already computed as the rise over the run. In other words, the sine of x over the cosine of x, which we called the tangent of x. So the tangent of x is the slope of this line, meaning that if you were to look at this larger triangle and notice that the base is 1, and you can think of that as being a sort of run, if you're thinking of the rise over the run, or the change in x of 1, and every time you change the x value by 1, you're going to be increasing by the value of the slope, which is the tangent of x. And so the length of this height here, of this red line, is the tangent of x. Okay. So now what we need to do is kind of make a quick sketch, highlight the different shapes that we're going to be comparing. And so the first shape that we're going to look at is the one involving sine, where we're going to use this, and this. So I'll connect that in a second. The next one is going to be this pi slice, and then the larger triangle. Alright, so there we have it. And what we should be able to tell is that the area of the blue is going to be in between the area of the green and the area of the red, no matter what the value of our angle is, of x is. And so what we just need to do is represent these areas algebraically so that we can manipulate them so that what we have in the middle is sine of x over x. So our task now is to find the area of the red, the area of the blue, and the area of the green shape. Alright, so just to think back, the squeeze theorem, we wrote the biggest function on the left. Remember we had f of x is greater than g of x is greater than, or equal to h of x. And here we're just going to go from smallest to largest on the left. So the first function that we're going to write is the green, the value of the green area here. And so what we want to know is this is a triangle, and we have the base is a value of 1, and the height is the sine of x. And so we have base times height divided by 2, and so that'll be 1 times the sine of x divided by 2, which is just going to be the sine of x divided by 2. All right, and that's going to be less than this blue shape here. Now, the blue shape at first might seem a little bit tricky, but notice that it's just a sliver of the circle. And the circle has a radius of 1, so the area of the circle is 1 squared 1 times pi r squared. So that whole area of the whole circle is pi, and how big is this sliver? Well, we know that there's a total of 2 pi radians, and this is x radians, so the sliver that we have is x over 2 pi. So the percentage of the circle we have is x divided by 2 pi, and we take that percentage, that fraction of the circle that we have, and we multiply it by the total area, and that will give us the area of this sliver, this blue sliver. So the fraction of it that we have is x over 2 pi. And we then multiply that by the total area, which is just pi r squared, or pi times 1 squared, which is pi. All right, now for the red, and this blue one is going to be less than the red area, and the red area is very simple, right? It's the base times the height over 2, 1 times tangent x over 2. Okay, and we can do a little bit of simplification. Pi divided by pi is 1. And so now we have our inequality written up, and notice that we have less than here instead of less than or equal to. That's fine, right? Less than is in fact, even better. All right, so let's notice something that will help us kind of clean this up just a little bit. And that is that each of these is being divided or divided by 2 or multiplied by 1/2. And so if we multiply the whole inequality by 2, each piece by 2, we will be able to cancel the denominator of 2. So we'll do that, and now we can rewrite. We have the sine of x is less than x, which is less than tangent of x. Okay. Now, we used areas to get these, right? And we always think of areas as being positive values, right? You'd never want to compute an area that's a negative area. But remember that sine and tangent, those can actually be negative values, right? And so if you think about this inequality here, what do you have to do to kind of preserve the fact that you're using an area? Originally, that's what we were thinking about. And since area is always positive, we want to say that this is true, right? In the first quadrant, all of these are positive. But if we were actually computing these in different quadrants, we'd have to make sure that we turned our value positive. In other words, we'd have to take the absolute value. So to make sure that this is true, in the fourth quadrant, in the second and third quadrant, what we want to do is take the absolute value of all of them. And we know that that keeps the inequality true because in the first quadrant, right, everything is positive, and so taking the absolute value won't be a problem. All right, now taking stock of where we are, notice that the function that we are squeezing, we have an x. We do not yet have sine of x involved in the function we're squeezing. So what could we do? Well, we could multiply by a sine of x to each of these, and that would get us a sine of x in here. But notice that that would have sine of x times x. And so that's not quite what we'd want, right? We'd want, a division. So what if we multiplied by 1 over sine of x? And notice what that will do is actually turn this into 1, right? So what we're going to do is we're going to multiply by 1 over sine of x, and we're actually going to want to make that positive as well. We don't want that to ever be negative. So what we're going to do is we're going to multiply by 1 over the absolute value of sine of x, which is the same as dividing by the absolute value of sine of x. Okay. So let's clean this up a little bit. Now on the left, we have 1, which is less than. Here we have x, the absolute value of x, over the absolute value of sine of x. And here we have the absolute value of tangent of x divided by the absolute value of sine of x. Now there's a little bit of manipulation that we can do here. Tangent of x is sine over cosine, so we can rewrite this as, I'll rewrite it as sine of x, the absolute value of sine of x, over the absolute value of cosine of x. And we're dividing by the sine of x. Now dividing by the sine is the same as multiplying your numerator, which is this now, by 1 over the sine, or 1 over the absolute value of sine of x. Running out of space there, but you can see. And so these will cancel, those are 1. And so what we're left with is 1 over the absolute value of the cosine of x. And now we're really honing in on what we want. We are squeezing, this is the function we'd be squeezing here, and this looks eerily similar to what we have in our limit, except that the numerator and denominator are inverted, they're in the wrong place. And so if you remember, and I'll show you this in a second, we can invert everything in our inequality. We just have to change the inequality sign, and I'll show you a little hint as to why that is. So you know that 1/2 is less than 2. If you inverted both sides, 1 over 2 inverted is 2 over 1 or 2. And if you invert 2 over 1, which is 2, you end up with 1/2. And so you just have to change the inequality sign, right? Now the right side is less than the left side. And so if we invert all of these sides, we just have to change the inequality. Now if you invert 1, you're left with 1. So you have 1 greater than. If we invert this x over sine of x, we'll now have absolute value of sine of x over the absolute value of x, which is greater than 1 over cosine of x inverted, which is just the absolute value of cosine of x. All right, so we're very, very close now. The only difference between the function that we're squeezing and the function in our limit is these absolute value signs. And so what we need to do is think about whether or not we actually need these absolute value signs. And if we think back to our squeeze theorem, remember the squeeze theorem says that this inequality just has to be the case for the values around the x value that you're approaching, which in this case is 0. So if I were to just quickly sketch an xy coordinate plane, and we were to think about, look, 0 is right here, right? And so if you're graphing, you know, sine of x or whatever it is, you can think about, right, what are the values that are close to 0? Well, it's the values just to the left and the values just to the right. Well, if we think about the ones just to the right going all the way to pi over 2, then ones to the left would go all the way to negative pi over 2. And the values in between here that we're concerned about now, well, this would be the first quadrant, right, to pi over 2. And this over here would be the fourth quadrant, right, to negative pi over 2, rotating in a clockwise fashion. And so all we need to be the case is that sine of x over x is always positive when we're in either the first or the fourth quadrant. And if that's the case, then these absolute value signs wouldn't actually change the value, and so we don't need to write them. And this is the case, right? Sine of x in the first quadrant is positive, as is x in the first quadrant, right? And so that's going to be positive. And if I were to go to the left of 0, right, over here, right, well, then the sine of x is going to be negative, and the x value is going to be negative. So a negative over a negative is going to be a positive. And so I don't have to write these absolute values. And in fact, over here, I don't have to write them either, because cosine of x, either in the first or fourth quadrant, is always the x distance, which is positive. So I don't need to write the absolute values for any of these. And so now I have 1 is greater than sine of x over x, which is greater than cosine of x. All right, see if you can take this now all the way and use the squeeze theorem to prove definitively now that this limit is equal to 1. All right, so to apply the squeeze theorem, we have the first part, which is the functions, one being greater than another being greater than another. And the second part of the squeeze theorem, remember, is to actually find the limit as x approaches 0 of 1 and the limit as x approaches 0 of cosine of x. And if they are equal to the same value, then that guarantees the limit as x approaches 0 of the function we care about, sine of x over x, is equal to the same value. So the limit as x approaches 0 of the constant function 1, well, that's just a horizontal line. It's approaching 1 everywhere. So even as we get closer to 0, it will be equal to 1. And the limit as x approaches 0 of cosine x, and this isn't hard at all. Cosine x is continuous everywhere, right? You can draw it easily without lifting your pencil off the paper, and that's so far how we've defined continuity. And since it's continuous at this value, then we can just plug this value in, right? When we plug in 0, we don't get an undefined value. So we plug in 0, and cosine of 0 is equal to 1, and so that is our limit. And so the limit of both of the functions on either side are equal, which means that the limit as x approaches 0 of sine of x over x is equal to 1. And there we go. We've proved it. Sometimes when you finish proving something, to show that you're done, you can write a little box and fill it in as such. It says that we're done. All right, and there we have it. So I'm going to give you a couple more to try on your own and discuss with your fellow classmates, and then we will look at a few more in class. All right, I know that was a little bit of a long proof. Here are a couple of questions to try. Evaluate the following limits either with the rules you learned or by creating a table of values. So a couple options there. And then a bonus couple of questions that I encourage you to spend some time on. The first is applying the squeeze theorem, and the second is to try proving that second fact that we learned at the beginning of the video.